Live from your local news leader, Matthew White, Amanda Brennan, and Central Illinois' most accurate forecast with meteorologist Adam Shawinski. You're watching The Morning Show at 9 on WCIA 3.
Welcome back, everyone, to The Morning Show. We're glad you're here. It's Monday, and we have another Wise Guys segment. Joining us is Paul Kwiat.
So last week, it was all about static electricity, and sounds like we're continuing that conversation now.
We are continuing it, especially since it's such dry weather that can really be a problem. So if we just put up the first slide, just a quick recap on where we are. So we know that matter is made of charges. It has protons, which have positive charges, neutrons, which have no charges, electrons, which have negative charges, and the electrons are the ones that can move around. And we also talked about this triboelectricity, which is if we have different types of materials and we bring them together, the charge will transfer, and particularly we rub them together, that can happen. And the next slide shows this sort of listing that we gave, and if things are more on the positive side here, like in the upper left, they want to give up their negative charges, and if things are on the lower right, then they want to take charges. So for example, hair is positive and rubber latex is negative. So if we come back to me, and I just take this balloon and I rub it on my hair, I'm going to be transferring the charges here, and we can see now that this is even going to then have an effect on your hair, pulling it.
Got the mad scientist look.
Okay, so coming back to the slide again. So one way that we think about these things as kind of a more advanced concept as a scientist is we think that the charges are making electric fields. So I have these electric fields that are pointing away from positive charges, pointing toward negative charges. And we can see on the lower left, when I have opposite charges, why the fields from the positive charge gets sucked into the negative charge. It sort of pulls the two together. And on the other hand, on the lower right, when I have two positive charges, they're like pushing against each other. They're repelling you. So we can kind of see why that would happen then, why they might attract or repel. And on the next slide, if we put charges on a metal, like on some sort of a conductor, they'll arrange themselves, but they tend to be more concentrated where there's a smaller radius. So wherever there's a smaller radius, I'll have more charge, I'll have a higher electric field, and in fact, if the electric field is strong enough, then it can actually rip electrons off of the air, and it can cause it to ionize. I can have breakdown, and I can get a spark through the air, which is what we, if we come back to us, which is what we experience if you like walk around on your carpet and your slippers, and then you get staticky, and you go near the doorknob, then you get a spark, right? Okay. So we can actually demonstrate that just a little bit here. So I have this device, and I'm just going to put basically kind of a transformer on top of a transformer. So it's going to make some pretty high voltage.
Oh, we're not going to get zapped, are we?
Pardon?
We won't get zapped by this.
Well, I'm going to get zapped just a little bit. So I'm just going to come in here and see we have a little bit of electric discharge that's coming out.
That's the stuff we like to see.
Right?
Oh.
Yeah, exactly right.
That's cool.
But on its own, it's just charging. It's charging up, but it's not discharging until I bring this close, and then the electrons are kind of flowing through me.
I see.
So I'm going to change this. I'm going to change this just a second. Oh. So instead, I'm going to put a needle on the top of this.
Gosh.
And the needle has a much sharper point. And when I do that, now the electric, for the same voltage, I'm going to have a much higher electric field. And we can see that now it's actually discharging on its own. So it doesn't even need us. It discharges at a lower voltage, actually.
What to happen if we were to run our hand over it?
Let's not get ourselves as part of this circuit. It's not a high current, so it would be okay, but we still don't want to have high voltage going.
It's purple. That's cool.
Okay, so now back to our next slide. So this was a kind of a preparation. So back to this triboelectricity. So air wants to give up its negative charge. It turns out aluminum does too, but not nearly as much. So if you have aluminum and air in close contact, the charge will tend to go from the aluminum into the air. And that happens when you have an airplane that's flying, because the airplane wings are aluminum. Actually, they're coated in paint, so it makes the problem even worse. And you get, as the plane is flying quickly through the air, then it'll get charged up. It gets charged up with a lot of negative voltage, maybe to over 10,000 volts, and that can really screw up all the radio and the navigation equipment. So you don't want that. So the question is, what's the solution to that? How do you solve that? Well, if you look at an airplane, at the back of an airplane, they actually have these little wicks, these points that are showing there. There's the kind of four pointing out the vertical part, and then the horizontal part. I put the red arrows also. So there's a bunch of these very small points, basically, and therefore you can discharge at much lower voltages. So that's great. That's how we protect the planes and the navigation equipment and the radio.
Is that why you're supposed to turn your phone off?
No, totally different. Okay, and then last sort of public service case, where you look at one more example of this. So if I have something like wool or cotton, those will want to give up their electrons to something like polyester. And it turns out this happens all the time when you get in your car. So if we just take the next slide, where we have someone who's in a car, maybe in wool or cotton pants, and they're sitting on the polyester, the vinyl of the car, what will happen is that they will tend to charge up. That's okay. If you're just in the car, you might notice it when you get out. What you don't want to do is when you're putting gas in your car, you don't want to go and sit back in the car, because if you sit back in the car, you can build up this charge, and when you come back out, you can cause a spark, and that could ignite the gas. And in fact, there was a study that they were just showing here. The Petroleum Equipment Institute found that basically 50% of the fires at gas stations where there's not an open flame occurred because the person got back in the car.
Wow.
And in fact, there was this last study that was done just a couple years ago, where they look at this and the charging, how much charge you build up. And you can build up on a typical car something like 10,000 volts just by having a typical like fabric going into a car. It's worse in the winter. It's worse because it's cold and it's dry. And so definitely, even though when it's more cold out, you would like to get in your car when you're filling up the gas, don't do that. It's dangerous. If you do use seat coverings that have conductive, some of them have conductive fabric, and then that makes the problem quite a bit better. So it reduces the buildup of charge by a factor of 3 or something like that.
Very interesting. Well, thank you as always for joining us this
Thank you guys.
Monday
Hope you can stay warm. Everyone else.
Yes, stay warm. Here's a quick look outside this morning at those cold temperatures. Still to come on the morning show, Adam has your full forecast. That's next.